Okay, great. Awesome. Yeah, so hi everyone. Welcome to Multimodal Weekly webinar series. Both for those attending live as well as folks who will be watching this later on YouTube. So this is a weekly webinar series hosted by the team over at TinyLLaVA. Just for context, we early stage AI startup building multimodal foundation models for video understanding, and this is an initiative that I've been running for 1 year. Every single Friday to basically learning about the latest work in like multimodal AI. Some of the topics that we tend to cover on a weekly basis include like new research in multimodal and foundation models, innovative application of multimodal in different verticals. Since we focus a bit more on video understanding, sometimes we have, I guess, developers and founders talk about some of the initiatives that they work on this space. And finally, we have partners and internal team members giving guides and tutorials on using our platform and APIs. In some of the recent session, we have pretty much a wide-ranging like researchers that come in and talk about their work, right, ranging from evaluation of language model, multimodal for audio processing, multimodal between like speech and text, data set for multimodal AI, open source project on multimodal LLMs. And this is something that I've been trying to do more, bring in more researchers because I feel like the field is moving super fast. So definitely just kind of curious to see. Basically do not want to miss the opportunity for them to like share their work with the community. So for today's session, we have two presentations. The first one is by Jiwoo Hong, currently a master student at KAIST AI. And he will give a talk called Resource-Friendly Single-Step Language Model Alignment with ORPO. Very excited to see this work. And obviously, TinyLLaVA, we have a pretty special connection with KAIST as majority of our team, either have go to school there or have some affiliation working with researchers from that institution. And on the second half of the webinar, we have Professor Lei Baichuan and his undergrad student Baichuan Zhou give a presentation on TinyLLaVA towards smaller scale large multimodal models. And this is also like a very cool research direction, right, towards building open source initiative that can rival the Gemini, the GPT-4V of the world. So super curious to see how, given like the academic environment, the team from Beihang can view this model. For attendees, please feel free to send your question on Zoom chat, and we'll have probably a short Q&A session after each speaker finish. So with that, I will stop sharing my screen. And Jiwoo, do you want to go ahead, unmute, and start your presentation?
Yeah, sure. Let me share the screen. Can I check if you can see the screen?
Yes, I can see it.
Yeah. Okay. Hello, my name is Jiwoo Hong, and I'm master's student at KAIST AI. And first of all, thank you for having me here. And I'm really excited to share my work and have some discussion around the recent alignment methods. So in this talk, I'm here to talk about the recent work of mine on the resource-friendly alignment of the language models. So the paper's title is ORPO, Monolithic Preference Optimization Without Reference Model. So let me continue with some introduction to the alignment, and I'll introduce my work on ORPO and some more extended discussion or works that I did by myself and with collaboration with other researchers around ORPO. And maybe we can go up to some interesting discussions. Okay, so let's start with the human alignment first. So by saying human alignments, we are saying in the context of LLMs, we are optimizing the LLMs to generate the responses which are preferred by humans. So recently, the language models are very capable of speaking out like fluent responses, but whether it is preferred by humans or not, that is like another problem. So human alignment methods have been kind of interesting field of study starting from 2019, and it is kind of really being focused starting from the 2023, which by the DPO paper. So as I mentioned, like from 2019, the preference optimization of the language models have been studied in depth. And conventionally, the reinforcement learning was like first method to try the human alignment of the language models. So by saying reinforcement learning, we need to do some supervised fine-tuning, which I will call SFT, to the pre-trained language model. And then you have to do the reward model training. So you have two models here, the SFT model and the reward model. And then we apply the reinforcement learning algorithm. For example, the proximal policy optimization, we call it PPO. Then the model, the active policy is trained to maximize the reward, which is in the direction of making the model to be more human-friendly and be more human-preferred way. However, by using reinforcement learning, it is kind of costly because, as I said, we need to do the SFT, we have to make the reward model, and we have to upload those two models on the GPU at the same time. So for this reason, reinforcement learning is kind of costly and a bit unstable. But recently, like 1 year ago from now, there was a really great paper called Direct Preference Optimization. Your language model is secretly a reward model. So in this paper, they pursue the same objective with the reinforcement learning. However, they are kind of using the reward modeling objective without RL, and they just directly fine-tune their language models to the binary preference datasets. So by saying binary preference datasets, we have the given prompt, and we have the chosen responses, which is preferred by the human, and there is a rejected responses, which is like relatively dispreferred by the humans. So if you see here YW means the chosen responses, and YL represents the responses that are kind of dispreferred in a relative way. So basically, this loss function from DPO is really easy and really simple. So it is kind of just making a log probability margin between the chosen response and the rejected response given the fixed prompt. So after DPO, there were a lot of works recently tried to make the alignment process more simple and more kind of in a direct way. So after PPO, there were the methods like KTO, DPO, IPO, and ORPO, and really recently, the simple paper. So except for PPO, they do not require the reward model during the training. However, if you see the yellow box here, there is we call it pre-SFT stage. This means that we cannot align on top of pre-trained language model directly, but PPO, KTO, DPO, IPO, and simple paper kind of requires the pre-supervised fine-tuning stage, for example, on the instruction tuning data sets. And by the reference model here is, so we want to align the language models on top of the SFT model. So to train, and in the PPO, DPO, KTO, and simple, you need to kind of exclude the simple, the DPO, KTO, IPO, and PPO. Those methods kind of require the measuring the KL divergence against the SFT model. So we need to upload the reference model in the GPU during the training. So if we compare a lot of methods, including ORPO, we can see that other methods are requiring the pre-SFT stage. So the natural question that I had from looking at the previous methods was that, so what is SFT doing actually in the context of preference alignments? So by saying SFT, we are doing teaching the language model to kind of imitate what we want in the data set. For example, if we have the instruction tuning data set with the prompt X and the response Y, what we are doing in SFT is just we want to maximize the log likelihood for the given prompt and response pairs. And by doing so, we kind of expect the model to learn the domain knowledge or the response styles or chat templates, those kind of things. So by doing SFT, we are kind of teaching something through the data sets. So what I did in the paper was that, so if we have the preference data set, we have the prompt and the preferred responses, which is the chosen responses I call, and the dispreferred responses will be called as rejected responses from now on. So if we do the SFT to the chosen responses only, as you can see, the SFT cannot kind of differentiate what is chosen and the rejected responses. The likelihood of the rejected responses is going up along with the chosen responses, which is not really like desired behavior in the context of alignment. However, in the context of language modeling or like solving the downstream tasks, jointly increasing log probability is often called as the generalization, even though we just train the model on the small subset of the desired domain. Like the general log probability goes up and the language model can do whatever, like in general. So we call it generalization. So SFT has a really nice feature of like learning the knowledge and generalizing over the desired domain. So what we want from SFT in the context of alignment is preserving the knowledge acquisition role of the SFT, but at the same time, we want to kind of differentiate the chosen responses and prioritize the chosen responses styles. So we want to penalize the unwanted styles, which is represented by the rejected responses in the data. So this is kind of core motivation that we had while working on the ORPO. So let's go through the methods, like actual comparison for the methods, including ORPO. So as I discussed like a few minutes before, the RLHF, which is represented by applying PPO to the language models. If we have the pre-trained language model, first we have to do the SFT on the, like, for example, instruction tuning dataset, and we need to prepare the special reward model for alignment. And we have to upload the reference model and the trained policy, the trained model on the GPU. So there are 3 models on the GPU, the reward model, reference model, and the trained model. So it is kind of heavy and kind of costly. And DPO kind of excluded out the need of reward model, and it is kind of like relatively simpler than the PPO, but still heavy because we have to upload the reference model and the trained model. However, in ORPO, we are directly aligning the pre-trained language models, for example, the Mistral or Llama 3, those kind of pre-trained language models to users' preference in the direct way. So to simply say how this is work, we are using the odds ratio, and which is the reason why we call ORPO as the odds ratio preference optimization. So by maximizing the odds ratio between the chosen and the rejected responses, what we expect is we want the model to adapt to the chosen responses in a stronger manner, but we are giving a weak penalty to the rejected responses. So by doing so, we want the model to prioritize the chosen responses when they generate, but the rejected responses to be kind of like pushed away. So let's go through the loss function. It is pretty simple because the LSFT, like the loss function for ORPO, it comprises 2 different kind of parts. So first part is the LSFT, which we discussed already. It's just maximizing the negative log likelihood. So it is kind of adapting the pre-trained language model to the desired domain. But what is kind of different is that we are doing SFT on top of the chosen responses only, so that we can kind of push the model to learn the chosen styles in a priority. So, and the second part, the LOR, is actually the special part for the ORPO. So if we have the log odds ratio and we wrap it up with the log sigmoid loss function so that we can kind of want the model to maximize the log odds, which is the chosen responses over the rejected responses. So if we minimize this LSFT plus LOR, then we are kind of doing pursuing the 2 objectives at the same time. So we are kind of expecting the domain adaptation from the LSFT, and from LOR, we are expecting the preference alignments. So Yeah, let's see what is the odds actually in this context. So I majored the statistics in the undergraduate, and the odds, this concept of odds came from the statistics. So if you see the multinomial logic models in the statistics, they kind of compares the odds of two events to explicitly measure like which one is more likely to happen. So I brought in the concept of odds into here. And as you can see, the concept of odds is defined by the p over 1 minus p. So p here is the just normal probability that we can think of. So the probability is mapped from 0 to 1. But since the odds is p over 1 minus p, it is mapped over 0 to infinity, which has a lot of wider range. So we have the odds concept here, and we kind of measure the ratio between the odds of the chosen responses and the rejected responses, and we cover it up with the log. So we call it the log odds ratio. So we are kind of measuring the odds of generating the sequence Y given the input sequence X. But as we know, if we just like make a product of the probability in the language models, then it will be really small. So we are averaging the log probability. So 1 minus p, by doing 1 minus p, we have the denominator, which is in the middle of 0 to 1. And by having that kind of loss, we are kind of expecting the model to prioritize the chosen response styles, as I said. And if you see the gradient of the OR loss part, which is the right side part here, as you can see. So there are two parts mainly. In the left part, which is the underlined with yellow, it is kind of penalizing the pairs which have the wrong predictions. So if the odds of the chosen responses are higher, like a lot higher than the rejected responses, then the left part, the yellow part, will get smaller. So model will get updated like in a like minor amount. However, if the model is kind of predicting that the rejected responses is internally more preferred by the model, then that prediction is wrong in our perspective. So the updates will happen like in a more larger manner. And what is really interesting is the right side part of this gradient function. So as you can see, there is a 1 minus p as a denominator for each gradient. So by having the 1 minus p, it is kind of amplifying the gradients in a dynamic manner according to the log probabilities actually assigned to each response parts. So this is actually a desired thing, and which is a really interesting thing for the training the language model. So by having the right side part here, the gradient for the rejected responses, we can understand this as giving a penalty to the reward model for generating the rejected responses. However, if we give like same amount of penalty throughout the whole training, then the log probability assigned to the rejected responses usually gets too large, so it is kind of being overfitted to the training dataset. However, since we have the dynamic amplifier in the denominator 1 minus p, it is kind of as the training proceeds, the chosen responses log probability will get higher, which means 1 minus p will get smaller, which will amplify the gradient of the chosen responses, and that makes the rejected responses penalty to be relatively smaller, which is kind of preventing overwhelmingly suppressing the rejected field. And this is actually a nice point, which helps the model to be more aligned to the preference data. Okay, so that was a like kind of simple overview for the methods of ORPO. And let's go to the experimental kind of results, which we compare our method to the DPO. So ultra feedback is the data set which has the prompt and the chosen responses and the rejected responses. And those responses are generated with a lot of models, including ChatGPT. And the API model kind of rates the preference. So if the answer is more helpful and harmless, then it is assigned to be chosen, and the other one will be the rejected response. So to compare into the DPO, we do the SFT on the chosen responses first for the pre-trained language model, and then we do apply the DPO on top of that as SFT model in the DPO's case. However, in ORPO, as we discussed in the previous slides, ORPO directly applies, use the ultra feedback data set to train the pre-trained language model. Okay, so we tried two different preference alignment evaluation, and first one is GPT-4. So by using IFEval, it is kind of asking the GPT-4 to compare the response of the trained model and the response from the GPT-4, which is called the reference answer. So we are just simply measuring the win rate of our model against the GPT-4. So to scale our method, we compare against the Phi2 series, and we applied ORPO to Llama 2, which is 7 billion model. And here, Llama 2 chat models are the models, the official checkpoints from the Meta. So it is not trained by myself. And the Zephyr series and the Mistral ORPO series are all based on the Mistral 7B pre-trained model, but Zephyr is trained from the Hugging Face team on top of the 200K instances of Ultra Chat and plus 61K of the Ultra Feedback. So to simply say, every checkpoint on ORPO is using only the 61K instances included in the Ultra Feedback, but these Llama 2 chat or Zephyr series, they are using a lot more data to train their model. But however, as you can see, both in IFEval 1.0 and 2.0, the ORPO series are exceeding other models in the same pre-trained base models. Oh, so I just saw the question here. Yeah, the difference between alpha and beta in Mistral and Zephyr models. Oh, so here the Zephyr alpha and beta model, they have the difference of the training data set. Actually, the Zephyr alpha has a lot more SFT data set, which is a lot more than 200K, and a lot more data for DPO. However, the Zephyr authors kind of find out that the quality of the data, both for SFT and the alignment, is really important. So they reduced the SFT data set to 200K and reduced the DPO data to the 61K, which are the Ultra Feedback and the Ultra Chat. And it is kind of done by filtering out some bad instances. And as you can see, the performance of Zephyr Beta is kind of stronger than the Zephyr Alpha. And for our ORPO Alpha and Beta, they use the Ultra Feedback, but for the Alpha model, it uses the same Ultra Feedback with the Zephyr Beta. However, for Mistral ORPO Beta, it is using the, sorry, it is using the clean version of Ultra Feedback made by the Argila IO. So it is kind of difference in the use of different preference data, and I'll discuss the importance of this data quality in the following slides. Yeah, okay, great. So we discussed on the IFEval, and if we go to NT-Bench, which is another really interesting benchmark for evaluating the instruction following models. So Mistral ORPO Alpha, Beta, and the Capybara checkpoint, which is announced after the paper, achieves really high performance. And as you can see, it is kind of achieving higher scores than the Llama 2 chat, which is a 70 billion model. And yeah, if we make a direct comparison to the Zephyr Beta, Mistral ORPO Beta is kind of really close, but we can think that the Zephyr Beta is using 5 times more training data, including the SFT data. Also, we tried the alignment evaluation with the reward model. So this reward model is solely trained on the Ultra Feedback, like no other data. So if we do the RLHF or DPO, we are kind of pursuing for the RL objective of maximizing the reward and retaining the KL divergence against the reference model. So we don't want the model to diverge to some degraded collapsing model. So by doing so, we are kind of by applying the RLHF and DPO, we want the distribution here, the SFT distribution, which is the blue one, to be moving toward the right side to maximize the reward. And as you can see, DPO and ORPO is doing a great job on moving the distribution of the SFT model, here the blue distribution, to the right side. So if you see the yellow one, this is the DPO's distribution, the reward distribution, and the red one is ORPO's distribution. So as you can see, ORPO is successfully shifting the reward distribution to the right side, which is maximizing the reward. So it is pretty much achieving what we want from doing the preference alignment. So there are some other like additional evaluations. So there is a benchmark called IFEval, kind of asking really like strict questions, like write your essay within 400 words, or do not use commas while generating the responses, those kind of prompts. So as you can see, the Mistral ORPO beta is achieving pretty comparable and competitive results in comparison to the MOE version of the Mistral, the 8x7B. So this was really another interesting result that we found during the ORPO project. Also, this table is from the SIMPO paper. It is comparing a lot of different alignment methods, and this is really great resource for the researchers in the alignment field. And as you can see, ORPO is achieving like generally the top performing in comparison to other methods in the Open LLM Leaderboard kind of comparison. And especially it is notable that in the GSMAK, which is the math dataset, ORPO is achieving pretty high scores in comparison to other methods. And yeah, these were the results that we could kind of discuss in the paper. But beyond the paper, I brought some like recent my works or recent kind of experiments that I did. So using the capybara dataset. So this capybara dataset is like a small set of multi-turn conversation, which has 7K instances, which is a lot smaller in comparison to the ultra feedback. And as you can see, only training the pre-trained Mistral model on the 7K instances resulted even higher empty bench and even higher alpaca eval. So on the 4A100s, it took me like 2.5 hours to train the Mistral ORPO capybara. And as you can see, with a high quality data set, you may achieve even higher, like even more than this capybara checkpoint. So this kind of highlights the importance of the quality of the preference data in aligning the language models with ORPO. Also, we did the collaboration with the Hugging Face and Argilla, which is Hugging Face now. So we kind of trained the Mistral MOE model, the 141 billion sized Mistral model on the the capybara dataset, the 7K dataset. So using the pre-trained MOE checkpoints and the 7K dataset, we achieved like closer or even exceeding the similar size model, which is the DBRX instruct, and the Mistral instruct, which is announced by the Mistral AI itself. So yeah, it took like 1.3 hours to train the 141 billion in the 32H100s, and which is pretty short time regarding the size of the model. And for another way of scaling the ORPO, so recently, like ORPO is thankfully added to the auto train method in the Hugging Face. So it is really easy to apply the ORPO. And the author of the auto train kind of apply the ORPO on top of the Llama 70B instruct. And as you can see, even though like it doesn't matter for you to use the pre-trained language model or SFT language model or instruct version of language model as a start point for the ORPO. So it is achieving higher results in comparison to the Llama 70B instruct. So it is really your choice to choose the base model. And recently, in collaboration with Hugging Face team for the diffusion and the Korea University, we kind of expanded ORPO to the text-to-image diffusion models, which is totally different modality. And we kind of applied the same idea to the diffusion models, and we kind of aligned try to align the diffusion models without reference model. So yeah, if we compare the loss function here, the ORPO loss has the SFT loss plus the weighted version of OR loss, which is directly making the margin between the chosen and rejected responses. But the proposed method in this diffusion paper, we call it MAPO, has the really similar setting. So L simple here is just the SFT loss function for the diffusion models. And this L margin is doing the similar thing with OR loss without the reference model, but weighted with the beta value. So diffusion models can also be directly aligned without reference model with the similar logic. So if you're interested in the image and like different modalities, you can check out this paper. So, oh yeah, these are the results. So if you see the MAPO for like our model, as you can see, it has a lot more detailed and like fine-grained kind of images. Yeah, so these are the contents that I have prepared today. And some of these two things are the things that I'm kind of thinking these days to think about some future work for the ORPO. So for the alignment methods, including ORPO, we are kind of making a margin between the low probabilities assigned to the chosen and the rejected responses, but we don't still know what is the ideal margin between the chosen and the rejected responses because the mechanisms for the different alignment methods, they are all different. And the way of the changes in the low probability, they are all different in the different alignment methods. But in the context of ORPO, we can kind of dynamically control how much margin we want to make between the chosen and rejected responses with the weighting value lambda. So like if we think about it, like by strictly prioritizing the chosen responses might be beneficial for kind of suppressing some misinformation, which is like, we can call it like hallucination, but it might lead to degradation in other benchmarks since we are kind of lowering the low probabilities for the tokens shown inside the rejected responses. So it is really important to question what would be the ideal margin for preference alignments, especially in the different contexts of different domains. And also, recently, there are a lot of works on making a good synthetic data, like, for example, the Magpie kind of paper. So impressive results with Capybara using 7K instances highlights the role of data in the preference alignments, especially in the ORPO. So, and the related works these days say that on-policy data is really good for preference alignment on the like DPO or PPO kind of methods. So it is really an important question to find out like how can we make the optimal preference data with AI feedback for different models. So these two things like regarding the actual margin that we want and making a ideal synthetic data, these two things I like would be really important question in the context of alignment these days, in my opinion. So I think it will be interesting to discuss with the people here. And this is pretty much all of what I prepared today. Thank you for listening.
Awesome. Yeah. Yeah, thanks, Jiwoo, for the very in-depth presentation. If you don't mind, I just put on some resources around the work on the chat as well. I think that'd be great. Just like, you know, the link to ORPO and the link to MAPO. Yeah, is there any like question for you in the meantime? I think it's a lot of material for sure. Great. If not, yeah, feel free to just put on them on the chat, and then you can answer the question, you know, asynchronously. And yeah, so I want to give Lei the stage so he can go ahead with his presentation. Yeah, you, if you don't mind, stop sharing the screen. So
Oh,
that
okay.
Hi, James.
Yep, I see it.
Can you see the screen?
Yes.
Okay, so let's. Is it work? Great. Okay.
Yep.
Oh, okay. Hi, everyone. Thanks for the invitation from James for the Multimodal AI webinar. So I'm Lei Huang, an associate professor from Beihang University of China. I will give this talk with my student, Baichuan Zhou. The title of this talk is TinyLLaVA towards smaller scale large multimodal models. So, it might sound contradictory because it has both smaller scale and large in the title. We will illustrate this point in our presentation. Besides, we will provide the details of how we build our smaller size large multimodal models, TinyLLaVA. In the last, we will show our simplified and modularized code base TinyLLaVA factory. Okay, let's show our motivation, why we want to train smaller scale models. So as everyone knows, large language models are essential technique in the AI communities, with the scaling laws serving as guidelines. Recent years have a trend towards scaling up model sizes with the large language models of thousands billion parameters. It seems that the size and computation of language models are increasing exponentially in natural language process communities. Meanwhile, in computer vision community, large multimodal models, or let's take a short over to LMM, are proposed to inherit the capability from LLM, usually by aligning vision perception to the language spaces. This pipeline has led to various LLM released with a massive amount of parameters, like Flamingo and Parmean. Despite the fact that scaling up model sizes can significantly enhance performance across various tasks, training such large models requires expensive computation cost, and their large sizes may need to unaffordable training baggage. This restricts research access to only well-funded industries and organizations. So, from a perspective of practice, this is not friendly for resource limited academic communities. Okay, from another view, why we need LLM and what functionality of LLM we want? Definitely, we don't want the large model size of LLM. What we want to is the unification of tasks in modeling. To illustrate it, let's move back to the history of artificial intelligence. In the age of feature engineering, for a particular task, given the input X, for example, an image, we needed to extract the feature based on the domain knowledge, and then get a effect with fixed length, let's say height X. We then use a machine learning algorithm to learn the map or the function between height X and the target output Y. In this age, we need the feature engineering because the simple machine learning method cannot well process the complicated inputs. For example, the variance length of texture sequences or the variance size of the image. So, in the age of deep learning, we can train a deep neural network end-to-end for a given task without using the feature engineering. In particular, with the progress of deep learning, we can train many tasks given various inputs and outputs end-to-end. But in this age, we need a different deep neural network for different tasks. In the age of LMs, we can unify various tasks using conditional models. That is, the autoregressive models, because we can describe the task efficiently by using language, and give the task description as the conditional input. We can solve any tasks. So in this way, we can unify various tasks. Moreover, the training is based on self-supervised learning, and we do not need explicitly label data size. Therefore, what we want to LM is not large, but the unification of tasks. This is why we want to do this smaller LM. Okay, following this philosophy, a large network that focuses on smaller scale LLMs has gained attention. For example, the 2.7 by 2 models and the 1.1 TinyLLaVA. These models, have potential abilities similar to its large counterparts, including the ability of language understanding, common sense reasoning, math code, and so on. These small-scale LLMs provide a chance for conducting smaller-scale LMMs. That's the main motivation why we built the TinyLLaVA. Okay, given our motivation, how we build the smaller size LLM? Our goal is to build a model with efficiency, and simplicity. So our solution, therefore, is following the design of LLaVA, but generalizes from it for better investigating the variance of the model architectures and tuning recipes in a unified perspective. So this is the framework of our TinyLLaVA, and we considering the design choices, including the architecture components, tuning recipes, and the scale of training data. Okay, so Lei Baichuan Zhou give more details.
Okay, sure. Can you guys hear me now?
Yep, I can hear you.
Okay, so sorry, wait a bit. Let me just share my screen. Okay, you guys can see my screen, right?
Yes, I can see it.
Okay, great. So let me take it from here. My name is Baichuan Zhou. I'm an undergraduate student from Beihang University, and I'll take it from here to talk about more on the technicality and details of training TinyLLaVA and the whole framework. So in this part, I would like to talk about the 3 primary design axes of our LMMs exploration with TinyLLaVA. So to build efficient and proficient multimodal models, we first want to explore different kind of choices in the vision and language backbones. We want to know what kind of combination of vision and language models make our final multimodal models tick. So in our paper, we chose CLIP and SIGLIP as our primary vision backbone. And so on the vision model pool on the left, you can see we chose SIGLIP and CLIP. And on the right, we pick 3 small-scale language models as our language decoders candidate. So from our model pool, we were able to conduct a series of experiments and confirm some valid insights. So first, we found that higher resolution and more visual tokens that do lead to better performance. We could just look at the chart on the below. So across different language backbone scales, we could see that models equipped with SIGLIP do yield better performance against model equipped with CLIP. So, which at that time was very different from the mainstream VLMs, because mainstream VLMs at that time mostly equipped their models with CLIP as their primary vision backbone. And our study here do provide some valid insights that switching to SIGLIP, you can enjoy some performance gains without increasing a lot of parameter count. And so the takeaway here is that resolution and visual tokens do matter in the field of small scale large multimodal models. And now let's look at how different language backbones and models perform under the same training data setting. So the takeaway here is language models do perform better with bigger parameter count in the same data setting. So in the chart here, we can see that TinyLLaVA equipped with CLIP do have the lowest performance against Phi2 or stable LLM. And the same thing happened here if you take a look at a chart with SIGLIP. So under the same training settings, very intuitively, our experiments do confirm that bigger models do have certain merits, and with different vision backbones, our hypothesis and still exist, bigger models do perform better. while that's true, we still want to ask ourselves the question like how to make smaller models better and how to compete with bigger models. So primarily we start our exploration with data. So like from a data perspective, we try to scale our training data. We hope that with more intensive data scaling, like maybe better and more higher quality pre-training data, our smaller models can perform better than the bigger models. So like in this part, we switched our pre-training data from the original LLaVA pre-training data, which only has like 0.5 million data samples, to the newly proposed shared GPT-4V pre-training data, which has 1.2 million samples. So like shared GPT-4V samples, they provide more and higher quality, like more detailed descriptions than the original LLaVA pre-training samples. And as it turned out, compared to the original counterparts, switching to shared GPT-4V do yield some better performance, and more data do lead to better performance, even for the little ones. And during the pre-training, significant improvements can be seen compared to the original counterparts. But like I said, our question is, can we make smaller models better than the bigger models, not just compared to its counterparts? So for example, if we take a look at the chart on the left, TinyLLaVA with shared GPT-4V as its pre-training data, we do observe some performance gains. But what we want is that TinyLLaVA trained with more data, maybe we can have better results than the stable LLM or maybe Phi2. So our exploration did not just stop there, because we want to show that superior performance can be gained against bigger models with like a more sophisticated choice of design space. So to do that, we explored another design axis, which is the training recipe. So basically, our intuition is, because we have observed that the samples in shared GPT-4V have good quality and very similar to the samples in the fine-tuning stage, we could try to unlock our language decoder during pre-training so that more knowledge and guidance can be manually injected into our small models. So in other words, we try to help models learn better by unlocking more parameters during pre-training. And we conducted our experiment in this part. Under the same data, under this shared data setting, we can see that the recipe indeed brought superior performance, like TinyLLaVA trained with the shared recipe and can beat bigger models like stable LLM and not Phi2, but maybe stable LLM. So like TinyLLaVA, it has like 1.1 billion parameter, and stable LLM have 1.6 parameter. And stable LLM with under the same recipe under the share recipe, we can beat like models trained with the base recipe, like with Phi2. So like with better design choices, we found that smaller models can indeed beat bigger models. So like we can look at the chart here, like TinyLLaVA trained with Siglib as its vision encoder can perform better compared to stable LLM trained with Clip as its vision backbones. So like we observed that multimodal models with 1.5 billion parameter count can be better than the 2.0 billion parameter count, and the 2.0 billion parameter count can be better than the 3.0 parameter count. And with our final design choices, like we trained with shared GPT-4V as pre-training data, we have more sophisticated training recipe, and we chose a better and superior vision backbones as our final model selection combination. Our 3.1 billion parameter count, finally, we show superior performance against like LLaVA 1.5 with 7 billion parameters. So the same stories happens with TinyLLaVA and Phi2 and others. And finally, we present our like TinyLLaVA, which is finally 3.1 parameters. And so like in summary, in our paper, we try to build better small-scale large multimodal models by exploring 3 primary design axes, which is model selection, data scaling, and training recipes. So We found that SIGLib can act as a better vision backbones than CLIP in the small scale settings. And we also find that better training data combined with better training recipes, smaller models can be at least as good as bigger models. So, and as indicated by our downloads here, by the span of the recent 4 months, TinyLLaVA indeed gained some attention from the community. And as of today, the TinyLLaVA series has been downloaded over like 80,000 times in the span of 4 months and continues to grow. And we're happy that our fellow researchers in the research community are using our models. So like in summary, our contributions can be threefold. So first, we provide very capable and very easy to use small scale multimodal models. And we provide a very simple and reproducible baseline for future research. We have 12 models in total, and we also provide some very detailed analysis on the design axis of the LMMs. And I really hope that our work can serve as like a moderate baseline for future research in LLMs and other fields. Also, I think my part wraps it up here, and thank you guys. I'll take it back to my professor.
Okay, thanks, Baichuan. Okay, let's share the screen. Okay, so let's continue to we spend 3 minutes to share our introduce our code base TinyLLaVA factory. So the main reason why we build this factory is that the training of LMs is quite complicated for practitioners. It requires various data processes and carefully collaborate between model architectures and training recipes. We believe a simple and easy use code base will benefit the community. So that's why we build the TinyLLaVA factory. TinyLLaVA factory is an open source modular code base for small scale LMs, following the design philosophy of factory pattern, with a focus on simplicity of code implementations, extensibility of new features, and reproducibility of training results. So it leverages the standard deep learning pipelines that starts from preparing data, preparing model, and to training and evaluating. So TinyLLaVA factory is broken down into 5 modules that can be interchangeable and manageable. It includes data, model, trainer recipe, trainer, and evaluator. So we aim to minimize the dependencies between these modules. So allowing each module to be scaled to new alternatives in a plug and play way. Okay, currently TinyLLaVA factory integrates popular small scale LMs range from 450 mm to 2.7 B. For example, the OpenEM 450 M and 5.2. So it also integrates mainstream training recipes, including frozen for or partial toning, LoRa, Corora, and so on. So we also provide the documents for providing the details of code base and ensure reproducibility for our trained model. So the demo can be found on this website. Okay, thanks. Okay. Thanks for it.
Awesome. Yeah, super cool to see, your mention of the code base. I think I also include that on the webinar slide, but I think that's yeah. Thanks for going over that again. Yeah, so I think that's a very comprehensive coverage of the model philosophy, as well as I guess like all the motivation and the future direction of TinyLLaVA. So really excited about this work, because I think it opened up a lot of opportunities, right, for researchers to continue to build up on it and integrating more models, more data, right, and more training recipe as well. Great. Is there any immediate question for Baichuan and Lei related to the presentation?
Cool. Okay.
Yeah, so maybe just one like maybe logistical question from my end is like, oh, you want to share something?
No. So I will just share the screen. Okay.
Yeah.
In case some question.
Okay, great. Thank you for hosting the whole webinar thing. I think it's great, pretty great. Thank you, James.
Yeah, absolutely. I guess, yeah, if in the scenario that actually I have one question before we end. Have you tested the model
Sure.
on video
Videos?
on video understanding benchmark yet?
Well, actually, no, we haven't tested our models on the video benchmark, but I think some follow-up work used TinyLLaVA as a backbone for video understanding. I think there are some great papers out there. Like I think recently, like there's a paper called Shot Lock Forms. Like this paper used TinyLLaVA as a multimodal backbone and extended to the video domain. We ourselves did not explicitly carry out this domain, this benchmark testing thing. Okay.
I see. Yeah, I'm curious because I know the original Lava framework, they also explore video, right? I think they have Lava Next, which is the new extension of Lava that was designed for video. Yeah.
I think the whole Lava Next series, they sort of proved that like native image understanding multimodal models can exhibit some zero-shot capabilities in video understanding. And I think TinyLLaVA shouldn't be any more different than that. I think, and I think more papers have confirmed that our native image understanding model also shares some zero-shot video understanding capabilities.
Makes sense. Awesome. Yeah, I think that's the only question I had. Because I think
Okay, cool.
Yep.
Cool.
Great. So yeah, thanks to you, thanks Lei and Baichuan for spending your time on Saturday morning your time, present your work. Thanks
It's an honor. Okay.
Yeah, thanks to attendees for sticking to the end. The recording of this webinar will be available within, I say, 3 to 4 weeks, and I'll be sure to share the YouTube link to the speakers when it's become available, so they can evangelize it with fellow researchers. Thanks, guys. Appreciate it.
Okay.
Thanks.
Thank you.
Enjoy the rest of your
I had a
weekend.
very good time. Thank you. Bye.